Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. All right. Hope you guys are doing well. We're going to jump right into it because we were in the middle of doing some examples last time, and I asked you guys to try to get through those. So let's go. Make sure I can see the chat here. All right, so we were doing limits. Last time we covered a bunch of strategies, and then I asked you to go forth, my children, and try these strategies and do these problems. So we're going to get through these guys. I am going to, we're going to see how we're going to do the strategies, how we want to approach them. I'm also going to tell you about one of the special techniques, another one that we're going to apply for these guys here that look crazy. And we'll stop that for now. We'll actually have one more special technique for limits, but we need more math in order to apply that one. So that's coming later, but that's what we're going to do. And if we finish the above, the next on the agenda is continuity. So yeah, I'm not sure if I expect to get to continuity today, but I might introduce it today, and we will do more stuff on it on Friday. So yeah. Boom. Let's start with the first one. That was the limit. Anyone did that? What do we get?
0.
You got 0. How did you get 0?
Plugged in.
Just plug in. Strategy 1, right? Try to plug in. If it works, chances are that's the answer. When we get to continuity, we're going to modify. I won't say modify that step, but we're going to have a deeper understanding of that step. But yeah, here you can actually just plug in. Yeah. So I just plug in 1 minus 1 over 1 squared plus 1. That's 0 over 2. So the answer is 0. Yeah, that's pretty much it. Just plug in. Yeah. All right. So that one, strategy 1 worked there. Let's move on to B. Ooh. What did we get for that one? Anyone try it?
I got -1/2.
You got -1/2. So how did you get that?
Well, first I plugged in and then I got 0 over 0.
Yeah.
And then I simplified after.
Yeah. So again, I gave you those strategies and I numbered them because that's kind of how I want you to think about them. I don't expect you to know right away at this point exactly how you want to do it. So I just gave you like heuristics for deciding what you want to do here. So yeah, in general, remember, the first thing you're going to do is try to plug in. Right? At this point, you realize you're going to get 0 over 0, and that, bad, right? So then you move on to step 2, simplify so we can plug in. Right? So this is what should be going on in your head. You don't have to write this out on paper, which is why I wrote it in a different color. But this is where you should be thinking. You see a limit, the first thing you try to do, can I plug it in? Can I just plug it in, right? That's what you look for first. Can I plug in 1? You're going to realize, 0 in the bottom. If I write that on paper, Jhevon's going to kill me. So no, step 1 is not going to work. So now you move to step 2. Okay, can I simplify so I can plug in? And so that's what you go to next. So how do we simplify this? Well, the bottom is a difference of squares, so that's 1 minus x times 1 plus x. Okay, and how does that simplify? What does that become after I simplify it?
-1/1 plus x.
-1/1 plus x. All right, and why is that? Because x minus 1 and 1 minus x aren't exactly the same thing. You can't really cancel right away. So you kind of make a short detour. Basically, you think of the x minus 1, you can factor out a -1 to write that as 1 minus x. Right? You could factor out the negative from the bottom also, but it's probably nicer to factor from the top. And then you can cancel those. So there is a -1 left over. And that's where that came from. Okay. So now we have this. And now you ask again, can I plug in now? And now you can plug in 1 because the denominator isn't 0 anymore. You cancel the problem. So yeah, at this point, you can plug in 1. So -1/2. Also, I do want to point something out. Going over the last example. So this is not a new example. I just want to point out some stuff here. So what I wrote in blue is what you should be thinking, what should be going on in your head. You don't need to necessarily write that down on paper. But there are some other things I would like to, at this point out. Yeah, so you don't have to write that out. I already wrote that out above, so I'm going to erase this now. So this is what, if I gave you this on a test, here's what a full solution would actually look like. You'll write those lines out. Now, I just want to point your attention to one thing. When you plug in, at the point we plug in, we say here, we take the limit, right? So I took the limit at this point, right? And that's basically saying I took the step to actually start evaluating the answer, and now I'm going to get a computational numerical result, right? So there comes a point in this process where you take the limit. What I also want to point out is that you keep writing the limit sign until you take the limit. So what I want you to notice here is that I kept writing this limit symbol, right? So the whole time while I'm simplifying, I keep putting it back, limit as x approaches 1, limit at x approaches 1, limit at x approaches 1. Because what I'm doing is I'm just rewriting the problem. I'm not actually starting to evaluate anything, right? So I keep writing the limit while I'm simplifying, but there comes a point where, oh, that's good enough. I don't have to simplify anymore. And at that point, I take the limit. Once I do that, I don't write the limit sign anymore. I took the limit. So I don't have to write the limit symbol anymore, right? So you'll notice at this point, that notation disappears, right? But until we get to that point, you have to keep writing the limit symbol, right? So it's actually very important that you do that. So I will, it probably won't be a lot, but I will deduct points if you don't write it out like that. like maybe I'll take off 1 point or something. So that's something that you should be aware of. There's a way that we express our thoughts logically, coherently, and this is it. You keep writing the limit symbol until you can evaluate the limit. And this includes while you're simplifying to rewrite the problem to get ideas of how you want to actually attack and solve the problem, you keep saying, I didn't take the limit yet, I'm just rewriting stuff. Oh, now I took the limit, so I can get rid of the limit sign. This is the answer, -1/2, right? Also notice, this is something that happens quite often. I don't know where it comes from, but the limit is right beside the function. I've seen students write things like limit x approaches 1. They write the equal sign here, and then they put the guy over here. Or they write the limit as x approaches 1 equals -1/2, or something like that. Wrong notation. You cannot write that. Wrong notation. Where the equal sign is matters. Right? So it's like you're not actually making any sense, It's like you're talking like Master Yoda at this point, and like, what? That's kind of weird, dude. You're not really saying anything. That's not how language works, right? So that's kind of some things I wanted to point out. So that's what a full solution would look like, and those are just some things I want you to be aware of how the notation works. And in full disclosure, I will deduct points if you do this. Probably not a lot, right? Not as much as I would deduct if you totally got the wrong answer or totally went off and did something else, but I will deduct something. So I just wanted to make sure I do that, right? So yeah, that's what B would look like, and that's how it should look when you're writing it out, what I write in white. So yeah, as I did mention, in tests, you'd have to show your work, etc. And so just in general, you should know, I do take the do as I do approach. So when you might think, what does it mean to write out my answer? How much should I write out? Do as I do. As much as I write out in class is how much I would expect you to write out on a test, right? So I actually write out the examples the way I would expect you to write them out. And if there's anything that you don't have to write, but maybe it might help with your thought process, I'll write it in a different color ink. So just so you know, right? What I write in white, which when I print it out for the notes, it'll be in black and the background is going to be white, is what you should be writing out on the test. So just in case there are any questions on, how you're going to be graded and how much work do you have to show and what it means to show your work, I just thought I'd mention that. So just so we're all on the same page, you know what I'm looking for, you know what I expect. I think we should know that. Okay. I'm assuming there are no questions on that. If you have any, you should ask. But if not, we will move on to the next example. Okay. All right, what do we do? So I'd like someone to not just tell me the answer, but tell me your thought process to get to the answer so we can all follow along. So boom, this problem shows up on a test. Walk me through it.
If you try to plug in the 1, you
Okay,
can't.
so hold on. Let me try. So the first thing is try to plug in x equals 1. Okay, you'd realize you would get 1 plus 1 over 0. Right, so that's not going to work. All right, so you tried that on a test and it didn't work out. What do you do now? Panic. Oh my God, I'm going to fail. I'm never going to get into med school. My parents are going to No, that's not what you do. you move on to doing what? What will you do this that doesn't work? Now what?
Try to simplify it.
Right, so the next thing you're gonna think, okay, so me trying to plug in ain't gonna work. So I'll move on to step 2, try to simplify. So I can plug in, right? So this is what's going on in your head. You're not actually writing anything out on paper at the moment. You just see this problem and you're like, oh, gee, if I plug in 1, which is the first thing you should think about, you always think first, plug in. You realize, if I plug in 1, that's bad. So if that doesn't work, what do you think next? Okay, can I simplify this to plug in? That should be the next thought, okay? So equals, and again, you write the limit symbol because you're not actually taking the limit at this point, you're simplifying. So how do we simplify that? Yeah, continue, James.
Yeah. So you would get x minus 1 and x plus 1
Where? In the
at the denominator.
in the denominator. So you get x plus 1 over x minus 1 times x plus 1. So, all right, yeah. All right, we're in business, boy. Okay, all right, so we got that. So this simplifies to, and I'm writing the limit again because I did not take the limit yet. X minus 1. Now what?
You realize you can't plug in because
You
you get
still
0.
can't plug in. So at this point, you're like, still can't plug in. Right, because you have a division by 0, it's still there. So now you're like, all right, I couldn't plug in the first. I tried to simplify because Jhevon told me to simplify. I simplified and I plugged in. It's still 0. No, now I'm going to fail. My parents are going to tell me. No, right? You're calm. You're not panicking. All right, so this doesn't work. What do you do now? Third.
Graph it.
You could graph, right? So now you're pulling out, you're going into special techniques and all that stuff. So here, we actually covered, this was last lecture. Where did I do the write out the strategies? Yeah. So step 1, you try to plug in. If that works, great. Step 2, try to simplify if you can plug in. That works, that's great. Step 3, special techniques. So this is based on what you're looking at. You're going to do that. We'll cover hopefully a special technique. I think we'll get to that today. So we'll cover some special techniques. A special technique might also just be you knowing about the behavior of the function and doing it that way. That can be considered a special technique, but it might be something else. And that special technique actually doesn't work in this situation because the numerator is 1, the denominator is x minus 1. These are both polynomials. So you're comparing polynomials to polynomials. So step 6 isn't going to work here. But you wouldn't get to that point anyway. So step 3 is a special technique, but you don't really have a special technique for this. So then you move to step 4 or 5, right? Which means you're going to do a graph or a table of values. So you don't kind of freak out. You just move on to the next step in the strategy. So here you're like, okay, that didn't work. So here, special technique is probably what you're going to ask yourself. Is there like a trick, a shortcut to this, right? We don't know one for this situation yet. I don't think we're ever going to know one for this situation. So this situation you have to worry about. We don't know one for this situation. So the fourth thing you're going to think at this point is graph or table of values if you don't remember or know how to graph the thing. Okay. However, hopefully this you would know how to graph because you should know how to graph 1 over x, and then 1 over x minus 1 is just a shift to the right. So then you're like, okay, that didn't work. So what I'm going to do now is I'm going to graph this baby. Okay. So this is this is at 1. That's where the new y-axis was shifted because it's shifted 1 unit to the right. The x is positive, so it just looks like 1 over x. So I know it's going to look like that. And it's going to look like that. Right? So now, what is your conclusion?
Infinity? Oh, no, it does not exist. I read
Does
it
not
as
exist should be your
coming from one
conclusion.
side.
Right. So you realize here, okay, limit as x approaches 1 from the right side of the function I'm looking at went off to infinity. The limit as x approaches 1 from the left side of x approaches negative infinity. So at this point, you're here, you would finally conclude, so this means the limit as x approaches 1 of 1 over x minus 1 does not exist. And you can write, say, one-sided limits don't agree. Yeah, so we've gotten to the answer, right? And this one seemed like a lot of trouble. Like we had to go through a lot to get to this answer. But essentially, that's kind of how your thought process should go. So you see a random limit, immediately just try to plug in a number. It didn't work. Doesn't work? Try to simplify so you can plug in the number. But sometimes that doesn't work either. So now you're like, I have to do a special technique, or I have to graph it, or do a table of values. So we don't have a special technique for this. So you immediately go to the next step and graph it. Hopefully you should know the graph for this. If not, you should be able to do a table of values. So graphing would be the recommended one in this situation, because that graph should not be something that is difficult for you. So I would say graphing recommended here, since this should be easy to graph. Which should tell you, if you got to this point and someone suggests graphing it and you think to yourself, how do I graph that again? That's bad. That means you need to go review your algebra. That's a sign that you should go review, okay? This is something that you should, at this point, know how to graph relatively easily. However, there was another option, but let me just kind of write that out, is the table of values. So the thing is, especially since by assumption you're not using a calculator here, you don't want to have to waste time computing stuff in a table of values when you don't have to. Graphing is going to be a lot quicker. But if you don't have a choice, you don't remember how to graph, you can't graph, maybe it's a little bit more complicated. Table of values is probably what you're going to do. And of course, to make sure that you're getting the right thing, what you want to do is the thing you're actually interested in should be like in the middle of the table somewhere, and you're going to approach it from both ends, from the top and from the bottom, which from the top, you can think of that as representing coming from the right. From the bottom, you can think of that as representing coming from the left. So eventually I want to end up at x equals 1, and I want to know, how is the y value behaving here? Right? So I want to approach 1, and how's the y value behaving? So you're going to plug in a bunch of numbers. How many? It depends. You just want enough so that you start to see a pattern, right? So if I'm coming from this side, I might pick 0.9, 0.99, 0.999, 0.9999, right? And you're going to realize that you start actually getting something larger and larger, right? So that's like 9 over 10. So here you get 10 over 9. Here you would get 100 over 99. Here we get 1,000. Wait, no, we're not doing 1 over x. We're doing 1 over x minus 1. So pro tip, you want to write that probably in the top line. It's x minus 1 is what we want to do. So you actually want to compute 1 over, someone's trying to get in the room here. So you actually want to compute 1 over 0.9 minus 1, calculate that, whatever you get. Then you're going to do 1 over 0.99 minus 1, 1 over 0.999 minus 1, 1 over 0.9999 minus 1, right? You're going to realize that you're getting bigger and bigger numbers here, which indicates to you infinity. And then you go from, I actually did this opposite. This was from the left. Usually you want to do the right on top, but table of values is just something I wouldn't do here. So I didn't even think through what a table of values would look like. Okay, for a little larger than 1, you can start off at like 1.1, 1.01, 1.001, 1.0001. You would calculate 1 over 1.1 minus 1, which is going to be positive. 1 over 1.01 minus 1, 1 over 1.001 minus 1, 1 over 1.0001 minus 1. You're going to realize that these guys start getting larger. This is from the right. Usually we do the right above. Okay, so right, and that would conclude, you'd realize, oh, from the top I'm getting larger and larger numbers, but they're all negative. From the bottom I'm getting larger and larger numbers, but they're all positive. So this can tell you from the left I'm getting to negative infinity, from the right I'm getting to infinity. The fact that these don't agree, so then you'd realize that these don't agree. And that is what tells you D and E does not exist. Okay, so that's how that one would go. So you see this, try to plug in, can't plug in, division by 0. Try to simplify, easy, difference of squares. Jhevon thought he could trick me. I see you're ahead of your plans, Jhevon. Then you're like, damn it, my plans have been foiled. Jhevon saw that I would do this and it's still there, it's still bad, right? So now you think, okay, what else can I do? Special technique, you go into your utility belt, a special technique. Okay, nothing's there, all right, graph it, right? All right, use the graph jutsu. And that shows you that D&E is what you would get. But of course, what I wrote in white is what you would write out. I'm just kind of explaining what I'm doing here. Okay. Where are we on? D. So hopefully that was clear. Boom. What do we do here? Well, of course, first thing you think, plug in? Nah. Division by 0. 2, simplify. So what do we think? How would we consider this? Can we simplify this? How would you simplify this? What are we actually doing here? Probably what I would recall is maybe, what is the absolute value of X? What is that again? So what is that?
positive x.
When?
When x is positive.
If x is positive. What else is it?
And can be also negative x when x is negative.
Negative x when x is negative. What if x is 0? What's the absolute value of 0? Question, what's the absolute value of 0?
Just 0.
0. Right? So that is what that function is. So probably what I would do in this case, as it's written, it's just not expressing enough information. So what I'd probably do at this point is let's rewrite. So I'd know how to graph or how to simplify our graph or whatever I want to do. Simplify graph, etc. Right? Because at the moment it's in a very condensed form that's not showing me all the information right away. So it's kind of hard for me to know how to proceed. It's hard for me to do the steps and actually know how they're going to pan out. So what I would probably do at this point is actually write it out, right? So I know that the limit is, well, there's several cases, right? Now, if my x happens to be positive, which means I'm looking at the limit as x approaches 0 from the right side, then my absolute value of x is just x, right? So that's if my x is a positive number. Now here, you can say, what if x is 0? But at this point, you would stop yourself and you'd be like, limit doesn't care about being at 0. Okay, remember that was a thing with limit. We only care about getting close. So even if you could calculate it, doesn't actually matter. Then you would try to look at the other side. So when my x is negative, the absolute value returns negative x by definition. And that's when my x is less than 0. Right, so now I just branch this out. The absolute value, what does that mean? Let me branch it out so I can see what I'm working with here. Then I can come up with a strategy. Now at this point, simplifying is easier, right? Because I can now see what it is I'm simplifying. So at this point, all right, now I know how to simplify. In the first case, I'm just looking at the limit of 1, right? So that's just the limit of 1. In the case that my x is positive, and in the case that my x is negative, I'm looking at the limit of -1. Okay? So what is the limit of 1? It's 1. How do we know? Well, Jhevon gave us these properties. Yes. Accidentally closed. Jhevon gave us these properties yesterday. Let's go back. Boom, right here. Limit of a constant is just a constant. You can also think of this as a plug-in thing. There's no x to plug in, so plugging in just gives you back what is currently there. But you can think of it either way. Either think of it as a limit property, or I'm actually doing the plug-in, but because there's no x, there's nothing to plug in, so it just stays the same. So notice that it's 1 if my x is greater than 0, but it's -1 if my x is less than 0. So what does that tell you about the limit? This guy, the original.
Does not exist.
Does not exist. Left and right don't agree. So, I mean, FYI, if for some reason it was difficult for you to know that's how you would handle the calculations, you could graph this relatively easy as well, just by once you realize what the absolute value is. So, you know, graphing, you know that absolute value of x is equal to, you know, it's x if x is positive, 0 if x is 0, and it's minus x if x is negative. So this, of course, means that if I take absolute value of x and divide by x, that's just going to be me dividing all of these by x. So in the case where x is positive, it's that. In the case where x is negative, it's that. And the case where x is 0, well, it can't be 0. This far can't happen. So then you realize, okay, but x over x is, of course, 1. So when x is greater than 0, it's 1. Minus x over x is, of course, -1. So that's that. And so now you can just graph it because you know what, hopefully, you should know what the graph of 1 looks like and what the graph of -1 looks like. So you realize that on the right side, my graph is a horizontal line at level 1. And on the left side, my graph is a horizontal line at level -1. And from that, you should be able to conclude limit as x approaches 1 of absolute value of x over x does not exist, right? Because the left and right don't agree. So it's a constant 1 on the right, it's a constant left on the, constant -1 on the left. Yeah. Couple ways to do that one. But the moral of the story is, of course, to do the steps that I've given you, you have to really know what you're looking at. It's kind of hard to do it with absolute values unless you kind of branch out and write out what the absolute value actually means. And then you'll know how to proceed. So there are times when you're given this strange function, you don't even really know how to apply the steps, even if you wanted to. The idea is rewrite that function into terms that you understand better. And that's going to be that one. So that one doesn't exist. By the way, we'll make use of this example later, about 4 or 5 classes from now. So remember him, or at least when we get there, I'll remind you. Oh, you remember that time we did this? Right. It's coming, right? Foreshadowing. Okay. So let's go to the next example, this one. So test 1 comes around, you open up the test, boom, problem 1, find this limit. What do? Panic, freak out. Oh, I'm going to fail. My parents are going to disown me. I'm not going to get into med school. No, you don't panic. Go through the strategy. You know, this is how I attack limits. First thing, plug in. Can I plug in? Right? So you go and you plug in x equals 0. What would you get? Well, you would get 0 on top. You would get radical 1 minus 1. That gives you 0 over 0. Can't work. Okay, so can't plug in. So 2, can I simplify this guy? Can we simplify this guy? Ideas? You can. I just want to know, do you guys remember how? Obviously, the denominator is in the issue. How can we deal with the denominator?
Wouldn't you multiply it by itself?
Multiply by itself? What do you mean?
Like you would do radical 1 plus 3x minus 1, and then you would make that like you would, and then you would multiply it by that fraction.
So if I took this and multiplied by itself, what happens?
Oh, you
What
would
was
just
that?
get a bigger radical,
Yeah, but that's just this guy squared,
right?
which we have a formula for that. You square the first term minus 2 times 1 times that term plus you square the last term. So this is actually going to give you 2 plus 3x minus 2, 1 plus 3x. Is that what you want? You'd rather deal with that denominator than the original?
Should we multiply with the conjugate? Conjugate.
The conjugate. What is the conjugate of that guy?
Instead of minus, we put like plus.
You put a plus, right? Now, when you multiply with a plus, what is that?
We end up with 1 plus 3x minus 1.
Right, difference of squares, right? So 1 minus 1, you end up with 3x in the denominator. I'd rather deal with that, right? So we're in a situation where we have a difference and there is a radical. So the idea, the strategy, which again, we haven't covered it in this class, but that's because this is something you would have covered in pre-calc and algebra, which I mentioned that you need to know for this course. You would know to deal with a situation like this and make it simpler, multiply and divide by the conjugate. You have to multiply and divide by the conjugate. That way you're multiplying by 1, you're not changing the value of anything. So yeah, that is the strategy here. I know to simplify this, I would need to pull out the conjugate. So this guy here is the so-called conjugate of radical 1 plus 3x minus 1. When I multiply and divide by the conjugate, I get difference of squares in the denominator automatically. Maybe at this point, I'd expect you to be able to kind of see this in your head. So I'm just going to write this in a different color ink. I probably wouldn't expect you to write this down on paper. Of course, do it if you must. Don't try to do stuff in your head and then get it wrong because you can't pull it off, right? You should know yourself and know what you can do in your head versus not. But I wouldn't deduct points if you didn't write this line. You would see here that this is 1 plus 3x minus 1 times radical 1 plus 3x plus 1. At this point, you notice that this is difference of squares, which is the whole point of the conjugation idea, to get a difference of squares or difference of cubes or whatever. That's going to be the limit as x approaches 0 of x times, remember I'm multiplying the top by the conjugate also because I don't want to change the value, but that's going to be 1 plus 3x minus 1 You just square each individual term and keep the sign in the middle. So ultimately, what you're going to end up with is the limit. So you write out that you multiply by the conjugate, and then your next line could look like this. Then you're going to realize, hey, this is multiplication, and we can cancel cross multiplication. The x cancels into the x. So, I mean, optional to write this out, I suppose. So you get 1 plus 3x plus 1 over 3. And at this point, we can plug in. That's going to give me radical 4 plus 1 all over 3. And what do we get here? That's 2 plus 1, which is 3. So you get 1 as the answer. Right? Notice that I stopped writing the limit sign because I actually just took the limit. I plugged it in. Yeah, and that's that one. So the step 2 helped us here, but you had to remember step 2 would involve knowing to multiply and divide by the conjugate. Okay, let me quickly bring you through these guys to tell you the trick here. So these guys are going to motivate, and then I'll let you guys go. We'll talk about continuity next time. These guys are going to motivate a trick that I want to write. I'll write it down clearer next time. So there's a trick for these as well. Notice that the x is going off to infinity. That's actually important for this strategy. Notice limit at infinity. Okay, that is what tells you that you can do this thing that I'm about to do. So what we're going to do is, of course, 1 automatically can't plug in, so I'm not even going to think about it. Infinity is not a number, so I can't plug it in. So step 1 is automatically off the table. So step 2 is we're automatically going to think, can I simplify this to get something else? And you can, when you notice it's a limit at infinity, you can do this kind of simplification. Yeah. What you're going to do is divide by the highest power of x in denominator. Always. It's always going to be the highest power of x in the denominator. Okay. And so what would that actually look like here? What I probably want to say is divide each term. So now I look in the denominator, I notice that the highest power of x is x to the 4th. So this is going to look like the limit as x approaches infinity of, I'm going to do 4 over x to the 4th plus x over x to the 4th minus x cubed over x to the 4th. 2x to the 4th over x to the 4th minus 3x squared over x to the 4th plus pi x over x to the 4th plus rad 2 over x to the 4th. Right? You will notice that this is going to simplify. So this becomes 4 over x to the 4th plus 1 over x cubed minus 1 over x over 2 minus 3 over x squared plus pi over x cubed plus radical 2 over x to the 4th. And here's what you're going to notice as well. Hopefully, based on what we looked at yesterday, infinite limits, what happens to 4 over x to the fourth? Well, the top is a constant, the bottom is growing. So this is like 4 times 1 over x to the fourth. We know that that's going to look like this, asymptotic to the x-axis. This guy's going off to 0. This guy's also going off to 0. This guy's also going off to 0. You're going to notice that this guy goes off to 0 for the same reasons. So you end up with 0 plus 0 minus 0 over 2, which is just 0. Right? Limit is actually 0. Now, for this one, you can do the same trick. Now, there's a shorter way to do this that I'll show you guys next time. But for now, I just want you to know we can do the same trick. But I'll write it down in detail next time. So what I would do is go here, pick the highest power of x in the denominator, which in this case is x cubed. And divide every term by that. You will notice that this actually simplifies into, well, 4 over x cubed minus 6x squared all over 7 over x cubed plus 2. You can then see that this guy is going to go to 0, that guy is going to go to 0. That guy is just 2. This guy goes to what? 6x squared, as x goes off to negative infinity, actually goes off to infinity. So essentially here, it's like you have 0 minus infinity over 2. What do you get? Well, negative infinity, of course. Right? So that would be the answer there. For this one, going to do the same trick. And this is going to illustrate the other case. Never mind. Okay. Same trick. I do want to emphasize, though, I can do this trick because limit at infinity. I don't want you to think that this trick is always valid. It's not. Because it's a limit at infinity. So this is going to be a special technique for limits at infinity, right? Which I'm going to generalize. I'm going to write it down neat next time, generalize it, and show you what you can do instead of this process. But this is, so I'm going to tell you the shortcut, the rule, but I want you to understand why that rule actually works. So divide by the highest power of x in the denominator. So that next class, when I tell you the shortcut, and you're like, well, why would that happen? You're going to, this is why it happens. I'm showing you why we can make that shortcut. Now you'll notice that it's going to simplify in a very nice way. That'll give you 17 because those guys are going to cancel. This will give you 3 over x plus 1 over x cubed. It's the word cubed. This will give you 5 over x cubed minus 1 over x squared minus 2 minus 2. You are then going to notice, oh, that guy's going to go off to 0. That's going to go off to 0. That's going to go off to 0. That's going to go off to 0 by applying the limit properties that I can do it in the top and bottom as long as I get a finite answer. It's cool. So now this ends up just being 17 plus 0 over minus 2. So negative 17 over 2 is the answer here. There is a shortcut for this. This is one of your special techniques. That we'll describe in detail next time, so stay tuned. The next episode. Okay. Unless I can kind of tell you right now what the trick is, you can notice that the highest power in this is the same in the top and bottom here. And notice that the answer is the ratio of the coefficients of the guys with the highest power. If you look at this one, you'll notice that the highest power in the top here, right? If I look at the highest power is in the top, and notice that it goes off to infinity. It becomes an infinite answer. That kind of will always happen. If you look at this one, you look at the highest powers, you'll notice that the highest power is in the bottom. It turns out you'll always go to 0 in that situation. Why? Because of this reason. If you divide everyone by the highest power in the denominator, you're going to have a guy left over in the denominator, but everyone in the numerator is going to go to 0, etc. Right? So I'm basically going to state that as a special technique that you can use, and then I'm going to show you what would writing out your work qualify as if you're applying this technique, because you don't have to write all of this out, right? Which is good. You're on a test. You don't want to waste time writing out stuff you don't have to. So we'll cover that next time. For now, we'll wrap up there. So next time, I'll just state this special technique, show you how you can do this problem, these 3 problems even quicker using a general method, and then we'll move on to continuity. So unless there are any questions, I guess that's it for today. Are we good? Okay. All right. Have a good rest of your day. I'll see you guys on Friday. So take care until then, and I will see you guys in the next one. Ciao.